All right, y'all. So let's get started. So we actually have finished covering all of the material that we are going to cover in Chapter 17. And so rather than kicking off a new chapter, Chapter 18, since we kind of covered a lot of ground in this chapter, I figured it would be good to have like a review day where we just kind of carefully go over what it is that we've discussed thus far. All right. The first thing that we're going to take a look at is how to determine the pH, if this decides to cooperate ever, is how to determine the pH of a solution of a weak acid here. In this case, propanoic acid. All right, and so for a weak acid, we're going to have to consider the equilibrium expression for this acid here when it reacts with water. Strong acids, we can just assume that the concentration of hydronium is the same as the concentration of acid, but for weak acids, we can't make that assumption, right? So we got to go the long way using the equilibrium expression in the ice table. We're going to have the same first three steps for a lot of these problems here. You're going to need first a balanced chemical equation. Then you're going to need the equilibrium expression. And how do we figure what to put into that equilibrium expression? What do we build? Ice table. Right? That's how we fill in our equilibrium expressions, is with an ice table. All right, so today's just going to be a bunch of practice problems. I'm going to give you guys a head start, see how much you can do here, how much we remember. You can go ahead, everybody take a second and introduce yourself to your neighbor. Kind of awkward. Hi, hey, hello, how are you? Awesome, they're going to be your best friend today, all right? Yeah, good question. I get my balanced chemical equation. For my equilibrium expression, I got this K value. Where the heck am I supposed to get the K value from? The table, right? So this is our constants page that's listed for this particular chapter. You'll need it to get through some of the worksheet problems here, but yes, I'll put it up on the board right now. Part of it is going to be looking up your particular acid, right? You don't want to just assume that information, every bit of information is given in the problem. We got to know where to look for certain pieces of information that we need. So absolutely, I need a Ka value. Where am I going to look? On our table here. Notice that they're listed alphabetically, and I will always give you the name of the acid in addition to the formula so that it's not like a spend forever trying to hunt it down kind of thing. This one was propanoic acid. You do have to have a balanced chemical equation. That's going to be our first step. All right, so we got a good question here. I need a balanced chemical equation. Obviously, a good bet is that I'm going to be using my acid, right? That's why it's given to me here. HC3H5O2. And when I'm talking about preparing a solution of acid, what is this going to be reacting with? What's my other reactant here? Water, okay? Look, we've talked about like chemical equations with acids and bases where we can spy what the acid's doing and becoming the conjugate base, what the base is doing becoming the conjugate acid. The only time that we've been working quantitatively with pH is just with solutions, where you always have your acid or base plus water, okay? So that's how I'm going to get my balanced chemical equation here. I'm going to react this with water. I then need to be able to get my conjugate base, right? If this is my acid, it's going to turn into the conjugate base. And this was one of the first things we learned how to do. Do I increase my formula, increase the number of hydrogens or decrease the number of hydrogens? Decrease. Remember, acids are donating protons. It's going to lose one of those protons. So this becomes C3H5O2. And am I done? What do I got to do? Somebody said it. Charge, right? So not only does my hydrogens decrease by 1, my charge decreases by 1 as well, right? Acid conjugate base pairs is one of the first things we learned how to do in this chapter. And then water in this case is playing the role of a base. So it's going to become the conjugate acid, where I increase the number of hydrogens by 1 and increase the charge by 1. All right, so that's how I would get my balanced chemical equation. Again, since I'm talking about a solution, I'm always reacting it with water. I get my conjugate base by decreasing the number of hydrogens on my acid by 1, decreasing the charge by 1. I get my conjugate acid by increasing the number of hydrogens on my base by 1 and increasing the charge by 1. All right, so I took my balanced chemical equation and I built my equilibrium expression here, stacking my products over my reactants. I omitted water, though, because it was that pure liquid, right? So its concentration is constant. So I don't have to include that in my equilibrium expression. I then built my ice table, starting with my initial amount of acid. I don't start with any of my conjugate base or hydronium ion, okay? And then since my reactant's being consumed in this reaction, it will go down by some amount. I don't know what that amount is yet, so I'm going to leave it as that variable x. And my products will increase by that same amount because this is all 1 to 1 to 1 in my balanced chemical equation here. All right, so every one molecule of my acid that reacts, I'll get one molecule of conjugate base and one molecule of hydronium ion. So then I combine these first two rows to get my equilibrium value, and now I'm going to turn around and plug these in to my equilibrium expression here. So I get Ka equals x times x, or x squared, divided by 1.25 minus x. Okay, and then what's the assumption that, what do I get to drop from this here just to make my life a little bit easier? The minus x on the bottom, right? Because x is going to be so small, it's basically going to be the same thing as x squared over 1.25. And then we looked up our Ka value before, the 1.3 times 10 to the negative 5. All right, now I just have to do some algebra, some rearranging, and solve for x. All right, just to kind of be clear about what that algebra would be, I'm going to take this right here. I'm going to multiply both sides by 1.25. Right? You can do anything you want to an equation as long as you do it to both sides. Right? So I'm going to multiply both sides by 1.25. Whoops. So that gives me x squared equals 1.3 times 10 to the negative 5 times 1.25. And then I'm going to take the square root of both sides, and that will give me my value for x. Oh, whoa, whoa, whoa. All right, so I got x and I'm done. Why am I not done? Because what is x, right? Again, this is like where we want to make sure to take a step back because we start doing algebra, we start turning numbers into other numbers, and it's really easy to get lost as to what it is that we just did. When we found x, what did we find? right? X is the concentration of hydronium ions. So if I had asked you for the concentration of hydronium ions, we'd be all set. But I didn't ask you for concentration of hydronium ions. I asked for pH. So we have to take the negative log of that value. All right, so the negative log of X is what I'm after here. That's my pH. What's up? This one right here? Yep, that's the, yep. Because I took the negative log of X, yep. Yeah, so if we look at our table here, right, this row here tells us what all of our concentrations are. So X is the concentration of hydronium ions at equilibrium. That's why for my pH, right, pH equals the negative log of the concentration of hydronium ions. That's why I'm going to take the negative log of X to get my pH. All right, so what if I ask you another question like, I got no room to do it. What is the concentration? Oh, no, crap. Good call. My bad, my bad. I thought I did, but I did not. Okay, JK, bag it up. Now I take the negative log. Okay, 2.395. Just making sure everybody's paying attention here. All right, thank you. Okay, but yes, I totally forgot to take the square root. So actually X, if I don't forget to do that, my X value is a little bit bigger, 0.00403. And so my negative log, my pH is 2.395. All right, what if I asked you what the concentration of acid was at equilibrium? Concentration of HC3H5O2. Everybody take a second and see if you can't find that based on what we did up here. All right, where could I look to find my concentration of acid at equilibrium? The ice table, right? Now I'm just going to look in this column here. At equilibrium, it's that 1.25 minus X. And if we take our 1.25 minus X, we'll see that it's 1.245968. All right. Which again is very close to that 1.25, which is why we were able to make that assumption that we made up here in our math, right? To just kind of discard that minus X on the bottom. Again, we could have kept track of it. It just would have made the math a little uglier. Since x is so tiny, we get to discard it. But yes, again, just kind of trying to hammer home what your ICE table is telling you, right? This is the equilibrium value of all of these concentrations. So if I wanted to figure out what my conjugate base was, that would be x. My hydronium ion is x. And then my acid is that 1.25 minus x, right? That's what our ICE table is telling us. All right, now I can sort of do this same type of problem, all right, but sort of like restate it a little bit differently. So what do I mean by that? All right, so on the one hand, this is like the exact same problem, but instead of giving you the Ka and asking you for the pH, I'm giving you the pH and asking for the Ka, right? Structurally, the problem is kind of similar, but we are going to have to be pretty clever here because we need a balanced chemical equation, just like we had before. But I don't actually know what my acid is, right? I mean, that's the whole shtick, is this is an unknown acid, right? So how am I going to get a balanced chemical equation for an unknown acid? What we're going to do is use this like generic formula for an acid, HA. This is our stand-in for an unknown acid, right? We don't know what A is. It's just kind of like a variable there. And if I'm creating a solution of this unknown acid, what am I reacting HA with? Water, right? So it's always your acid plus water. Okay. I'm going to get my hydronium ions like I always do. How would I get the conjugate base of this acid? Everybody take a second and see if you can't concur with your partner what the formula would be for the conjugate base here of this generic acid. Same process that we do to find our conjugate bases all the time. All right, when I do my conjugate base, am I increasing or decreasing my number of hydrogens? Decreasing. And when I give my conjugate base, am I increasing or decreasing my charge? Decreasing, right? So my conjugate base would just be A minus. All right, so again, this is just how we can do this general formula for an acid, HA, where A is, we don't know, right? That's the whole idea. But it's an acid, so we know it's going to donate a proton in this reaction. So now we're going to do the same second step as before. We're going to build an equilibrium expression. All right, and then once you have that, you're going to build your ice table. All right, so I got my equilibrium expression. I got my ice table. If I plug everything in, oh, whoops. All right, and in the previous problem, I was given Ka, so that would have been, now I just had that one missing variable x, and I could solve for x, right? But here I'm not given Ka. I'm told this is an unknown acid. So how am I going to go about this problem? What am I going to do? What else am I going to use here? The pH. How am I going to use the pH? What is the pH going to tell me? The concentration of hydronium ion. Remember, pH, concentration of hydronium ion. They're one and the same thing, right? If you have one, you can always find the other, right? It's just kind of restating that concentration on a log scale. Okay, we said that pH equals the negative log of the concentration of hydronium. But what's the inverse of this equation here? If I want the concentration of H3O plus. All right, so truth be told, good news, it's on your constants page. All right, it's not something you have to have memorized, but we do need to recognize when we use it, this would be the 10 to the negative pH. That's the inverse of that equation there. Right? The inverse of a log is to take 10 and raise it to that power. Okay. So my pH was this negative, what was it, 1.73. Okay. And my concentration of hydronium, remember, is that X value, right? So that means that X is equal to 10 to the negative 1.73. I can turn around then and plug that into this equation here. right? So I got my formula for pH here. According to my ice table, my concentration of hydronium is just my X. So that means I can plug that into this equation here and solve for my Ka. All right, and then I'm done. What did it ask me for? The pKa. What the heck is the pKa? Just the negative log of the Ka. Okay? On our constants page, wherever the heck that is. What's listed are the Ka values. All right, you can find an equivalent chart where instead they're listed as pKa values, right? Again, if we have one piece of information, we can always find the other. That P is doing the same thing that it's doing in the pH. We're just going to take the negative log of the Ka. That's what our pKa is. All right, so the negative log of that value. Oops. .32, yeah. There we go, 3.324. All right, so I just want you to kind of compare and contrast this problem with the last one. The basic kind of format is the same. The difference is what piece of information you're given versus what you're being asked to find. Right? In the first one, you were given the Ka and you were asked for the pH. In this one, you're given the pH and you're being asked for the Ka, right? But you still need your balanced chemical equation, your equilibrium expression, and your ice table to do it, right? Same three components. All right, let me get a good example here. CNO.
I said today. You want to check? Today.
All right, so now we're going to do this solution of weak base here. The pH of a 2.25 molar solution of this weak base, the cyanate ion. Everybody take a second and copy this down so I can put up our constants page. All right, and you're going to give me these same 3 steps.
I know it makes you feel some type of way.
All right, so again, I'm talking about the pH of a solution, so I'm going to be reacting my weak base with water. Okay? How am I going to get my conjugate acid? What am I going to do to the formula of my base here? I'm going to add an H to it, so this is going to become HCNO. And what's going to happen to that charge? Is it going to go up or down? It's going to go up in this case, right? So it's just going to be HCNO. And then what's my other product for a basic solution? Hydroxide. All right, so now I got my equilibrium expression. For bases, we call it a Kb. All right, and how am I going to get the value for Kb? Where am I going to look? Constants page. So I'm going to go down to the bottom here where I have my bases listed. And what's the problem? It's not there. Uh-oh. We're screwed, right? Done. Call it a day. No. Okay. So this is the very last thing that we learned last class was the idea that a weak acid, its conjugate base, is a weak base, and vice versa. So what's listed is not my actual base, but the Ka for its conjugate acid, cyanic acid. All right, so how am I supposed to use that? Because that's a Ka, not a Kb, right? Let me just make some room over here. There is a very simple relationship between a base and its conjugate's acid's equilibrium constant. The Ka for my conjugate acid times the Kb for my base is always equal to that same magic number, 10 to the negative 14. So in this case, I can't find my Kb for my base listed, but I can find the Ka for my conjugate acid. And so I can use this simple relationship here to figure out what that Kb should be. Kb should be. All right, so my Kb is that 10 to the negative 14 divided by 2 times 10 to the negative 4. Okay, everybody take a second and do this. Follow along with your calculator here. All right, importantly, one very easy way to screw this up is whenever you're dividing by a number in scientific notation, what am I going to have to do when I punch this into my calculator? I have to put this in parentheses or it's going to totally gunk up my order of operations. All right, so if you do this in your calculator correctly, we should get 5 times 10 to the negative 11. Teeny tiny number. All right, so now that we've got our KB, I believe in y'all. Take this to the end for me. All right, finish up this problem by completing your ice table and then using that to solve our equilibrium expression, and then finally report the pH of this solution. Higher than I thought it was going to be. All right, so we're going to run out of time here. So what I'm going to do is I'm going to kind of quietly fill this in up here, and if you get stuck, you can look up and see what I'm doing, all right?
Yeah, I didn't.
You should not. Don't believe in rounding. It's bad for you.
How was that all? No, not at all. Okay. I'm thinking about that. They're not an ally. They're just a regular goodbye. You're not an ally. That is the half-eaten potato. Zoe, what are you doing? That's not a heart. That's a half-eaten potato. That's Roberto's word. No. Don't call me on that. That's a valid question. Is it?
All right, so I get my ice table, fill that into my equilibrium expression. I get my x, and then I take the negative log of x, and I'm done. No, why am I not done? That's the pOH. Remember, for a base, x is equal to the concentration of hydroxide. So this is not my pH, but my pOH. But I can use the fact that pOH plus pH equals 14. That tells me that my pH is whatever 14 minus that is, 9.03. Cool. Nice. What was your question over here? Yeah, cool. You good?